Okay, so last topic of the unit, and this one has pretty much no relationship to anything we've been talking about so far. It's just, where do I put this? I guess here. So, this is a little bit different. You're just, it looks scary, and it's really not that bad. There's just a lot of, it's all going to be completely brand new. Okay, and it's really, like I said, it's not that bad once you understand what's going on here, but it's just, metal complex, coordination compound, all of these big, scary words, and these big, scary molecules here, everything looks very complicated. So, we're not doing a whole lot with this. The AP exam doesn't test very heavily on this, so I'll just give you a general overview of what's going on here. And then maybe on Monday, what I would like to do on Monday, if we have some time, is just maybe show you examples of a few of these and what they look like in solution, because they're actually, most of them are very pretty. So metal complex, just some terminology you need to learn here. You know how I told you that metals don't usually participate in covalent bonds? Remember that from last year? Yeah, I lied a little bit, okay? They actually do sometimes participate in covalent bonds, and these are called metal complexes, okay? And so you've got, like maybe a central cobalt atom bonded to a whole bunch of other stuff, and the weird thing is, not only can it be bonded to other atoms, but sometimes it can actually be bonded to other molecules. So if you look at this is an actual NH3 ammonia molecule, and this ammonia is bonded to this cobalt. And so you've got four ammonias here and two chlorides that are attached to this cobalt. And so, just a little bit strange, right? And we're not used to seeing things like that. We usually think of metals as being these ionic bonded things. If the complex has a charge, so if overall this thing has a charge, then we call it a complex ion, okay? And compounds that have complexes in them are called coordination compounds, all right? So a metal complex is when you have a central metal and you've got some things covalently bonded to it. If there's a charge there, that basically makes it a polyatomic ion, a really big polyatomic ion. We call it a complex ion, okay? And then any compound that has these in them, they're called coordination compounds, okay? All right. These things are going to be soluble in water because they're actually ions, right? So we've got ion-dipole interactions here in these things. Sorry, something going on here with my headphones. They're all tangled. So this is sort of like putting sodium chloride into water, right? The water pulls apart the ions, surrounds them. Okay, the same thing is happening here because if these things have a charge, then the water is very attracted to them. It can pull them off and surround them, and then you have these ion-dipole interactions. So complex ions are going to be soluble in water. When we have molecules coordinating to the metal, in other words, covalently attaching themselves to the metal, they're called ligands. So if you look back over here, okay, in this example, the cobalt is the metal atom that's in the center. These are the ligands, the chloride ions, and then the NH3 molecules are also ligands, because those are the things that are attaching to the metal. Okay, here's some examples of some very common ones that you might see. H2O is actually a very common ligand. So is ammonia, which you saw on the other slide. Chlorine, cyanide is another one. There's several others, okay? To be a ligand, usually they're going to be anions. They're going to have a negative charge, like chloride or cyanide, or they need to be fairly polar molecules. And usually, if not always, I can't think of an exception to this, they're usually going to have lone pairs of electrons, like this, okay? That's kind of an important thing for being able to form a metal complex like this, is they need to have those lone pairs of electrons. All right. So many coordination compounds are brightly colored. I should have a picture of these instead of just having color orange, purple, green, violet. But notice, these are all cobalt chloride, okay? And so depending on the way that they form the coordination compound with ammonia, whether they bond with 6 ammonias, 5 ammonias, 4, or 4. Well, this is a cis-trans thing going on here, so it has to do with the shape of the molecule. That will actually affect the color that it turns in the solution. Okay, and so I mean, based on, it's really interesting how you can just tweak a tiny little thing and you can actually completely change the color of something from green to violet just based on the shape of the molecule. If you take any higher level biology classes, you're going to learn that structure and function are very much related to one another. So the shape of the molecule changes, the function of the molecule is going to completely change because its properties change, which is a very interesting, it's one of the reasons I like organic chemistry, is because it talks about that. Okay, so this is how coordination compounds were kind of discovered. This is a fairly new field within the last 100 or 200 years. I mean, I guess that's relatively new. But Werner is the one who came up with this, okay? And before him, this was the original way that these were written, okay? And so actually, let me go back to this slide for a second. The way that these used to be written, cobalt chloride with 6 NH3, cobalt chloride with 5 NH3, cobalt chloride with 4 NH3, or with 4, right here, scientists couldn't explain why sometimes this cobalt chloride with 4 ammonia bonded to it was green, and then it was sometimes violet, okay? Because it looked like the same thing. And so Werner was the one who kind of figured this out. And he came up with a new formulation here, which I think I put this on your notes also, okay? What he realized was these are basically forming ionic compounds, okay? And so you've got these complexes, these complex ions here, and then some of the chlorides that are in this compound, some of them were free to dissociate when you put it into water, okay? So you know how we talk about ionic compounds. A normal ionic compound like, what's a good example here, like MgCl2 or something like that, okay? When you put that in water, it's going to dissociate, right? It's going to split apart into how many pieces? Into 3 pieces, right? It's going to split apart into Mg2+, Cl-, and Cl-, okay? What Werner realized was, depending on how these compounds were structured, they would actually break up into different amounts of chlorine, okay? And so, and the way that he tested that, I feel like we've had a few problems like this. Do you guys remember talking about precipitating things using silver? Precipitating chlorine using silver specifically? So what they could do here is what he did with these compounds is he was using silver. He was putting this into silver ions and seeing how many moles, it's too early this morning, how many moles of silver chloride he was getting out, okay? So when he put this top one in, okay, with the 6 NH3s bonded to it, he ended up getting 3 moles of aluminum chloride for every 1 mole of this that he had, okay? This one down here, he would get 2 moles, it's not aligned this one. I'll just talk about it. The second one down here, he would get 2 moles of silver chloride for every 1 mole of this that he reacted, okay? And then for the bottom 2, he would get 1 mole of silver chloride, okay? And scientists were later able to sort of figure out that the difference between those last 2 had to do with cis and trans configurations, because when Werner started drawing the structure of these, he kind of realized there's 2 possible orientations for this thing in space, and he thought that probably accounted for the green versus the violet color, okay? Again, a lot of this is, you know, really foreign, really weird seeming. What you have to do with this on the AP exam is not so bad, okay? But his approach correctly said that there would be 2 forms of the COCl3 with the 4 NH3s bonded to it, okay? So you could think of one like this where the chlorines are on the same side, right? Or you could think of one where they're on opposite sides. So this is cis, this is trans, right? And so based on those 2 structures, Werner said just depending on whether the chlorines are completely opposite each other or whether they're right next to each other, that affects the color of the solution, okay? And so because his theory was able to correctly predict what was going to happen with these solutions when you put them into water and what color they would change, it became accepted as the best way to think about these compounds. Okay, so the way that we write these now, again, this looks very daunting, but you just have to think about this right here. That's a polyatomic ion, okay? And the entire thing here is an ionic compound. You guys see that? So this whole polyatomic ion right here overall has a 1+ charge. The chlorine has a 1-. So when you do your crisscross or whatever, it's a 1-to-1 ratio for each of these things, okay? You've just got to think of this whole big piece right here, this complex ion, as just a polyatomic ion in an ionic compound. Okay? So let's look at a sample problem here. Palladium-2 tends to form complexes with a coordination number of 4. Okay. Any idea what I mean when I say a coordination number of 4? Probably not at this point. Okay. If I look back over here, I'll give you a hint. This cobalt right here has a coordination number of 6. Okay. And all that means is how many different things are bonded to the central metal atom, right? So we've got a chlorine here, that's 2, 3, 4, 5, 6, okay, because we've got 4 ammonias also connected to it. So it has a coordination number of 6 here, okay? Now this one, the one that they're giving us in an example, has a coordination number of 4. That means there are 4 things bonded to the central metal atom. Okay, what is the central metal atom here? Palladium-2, right? Okay, they're even telling us the charge on this one. One such compound was originally formulated as PdCl2.3NH3. And we want to suggest the appropriate coordination compound formulation for this. Okay? So, the way that we would write this now, according to Werner's theory, we can only have 4 things bonded to the central atom, the central metal atom. Now, how many other pieces are there here besides the palladium? Yeah, this is just very unusual to look at. I've got 3 ammonias, right? But then I've also got 2 chlorines, 2 chlorides. You guys see that? Okay, so overall there's 5 things there. Alright, but only 4 of them can be bonded to the central metal atom. So the way this is probably going to work, if it's similar to the one that we did before, I'm going to write it like this. The complex ion goes in brackets. Okay, so I'm going to say palladium. And then I'm going to say that's bonded to all of the NH3s, which we have 3 of those. And then I'm also going to say that it's bonded to one of the chlorides in my brackets. And then I'm going to put the other chloride outside the brackets. Okay? Now, I don't know that you would have come up with that on your own, but does that kind of make sense now that you're looking at it? Okay? We've got the 3 ammonias attached to this palladium, and one of the chlorides is also attached to the palladium. This chloride is not attached to the central metal atom. This is just ionically bonded to this. Okay? So this is our complex ion right there. PdNH3,3Cl. And overall, this polyatomic ion would have a charge of 1+. Okay? And then this chloride outside the brackets has a charge of 1-. Those 2 come together, form an ionic compound, and that's that. Okay, does that kind of make sense? Hopefully the more you look at these, the more they make sense. It's just, they're daunting at first because they look so weird. Okay. So, suppose an aqueous solution of the compound is treated with excess silver nitrate. How many moles of silver chloride are going to be formed per mole of PdCl2, 3NH3? Okay, so what we have to think about here, how many of these chloride ions here are free to dissociate when we put this into water? Just one of them, right? Okay, so for every 1 mole of this that we put into water, we're going to be able to make 1 mole of silver chloride. Does that make sense? Okay. Now, if there were 2 chlorines out here, like some of the ones in the cobalt example, then we'd be able to make 2 moles of silver chloride. Okay. But because there's only 1 free chlorine there, the other chlorine is actually covalently bonded to the palladium. Okay. So that one can't. That's not free to react with the silver chloride. It's going to stay bonded with that, like all the polyatomic ions that we've learned so far. Okay. Those don't. Remember, polyatomic ions, they don't come apart when you have an ionic reaction, right? Okay. All right. So this is going to be 1 mole of AgCl made per 1 mole of PgCl2.3NH3. Okay, now we need to talk about Lewis acids and bases. This is a different definition of an acid and a base. It's a little bit broader, okay, than the Bronsted-Lowry definition. Bronsted-Lowry, they said that an acid is a proton donor, right? And they said that a base is a proton acceptor, which, when we say proton, we basically mean H+, right? You guys remember that? If hydrogen gives away its 1 electron, it becomes H+. It's essentially just a proton at that point, okay? So Bronsted-Lowry, they said if something can give away an H+, it's an acid. Like HCl has an H+, okay? If something accepts a hydrogen, then it's a base, okay? And that definition works pretty well for most things. Lewis wanted to expand that definition just a little bit because there were some reactions that he saw that looked like acid-base reactions that weren't, they didn't involve a transfer of a hydrogen at all. They actually just involved a sharing of electrons, okay? So basically, in a Lewis acid, you've got an electron pair acceptor. So Lewis acid always has a completely empty orbital, and the Lewis base is going to have a complete electron pair, okay? And those 2 things will just come together because the empty orbital on the Lewis acid is a perfect place for that electron pair on the Lewis base to fit. Okay, so they just kind of fit together like that. So in a normal covalent compound, you've got 1 electron in each orbital, and they come together and form a compound. In a Lewis acid and base, there's 1 completely empty orbital, and then the electron pair from the base comes in and fills that orbital. Okay. So an example of that, NH3 and BF3. Whoops. I guess I'm going to actually write that one for you. All right. So NH3 here. Well, first of all, let's talk about BF3 for a second. Okay. Boron trifluoride. Remember, that's one of those things. Boron's okay with 6 valence electrons, right? It's kind of an exception to the octet rule. So if we draw the structure for BF3, and I'm going to draw it like this. We wouldn't normally draw it this way, but this is the best way for me to draw it to make them fit together at the end. Okay, so that's your boron trifluoride, right? And then NH3 is going to look like this. If I draw the Lewis structure for NH3, that's what it looks like. Well, that looks like a good match, doesn't it? Okay, you see how that works? So, which one's my Lewis acid here? The BF3 is going to be my Lewis acid because that's the electron pair acceptor, right? That's the one that's going to accept the electron pair. The electron pair donor is the NH3 because that has the extra lone pair of electrons, okay? So these 2 things are going to come together, and I don't have any room down here, but let me draw up here kind of what this structure would look like. I mean, you can probably imagine it at this point, but it would form this compound here, BF3NH3, okay? And so when that happens, because this electron pair is, you know, coming over to this boron, so now boron actually does have 8, okay? Which it's okay with 8 too. It was okay with 6, but it's probably better with 8. And so then you've got this new compound here, and this is actually, according to Lewis, this is an acid-base reaction, okay? Which, that doesn't look like any acid-base reaction we've ever talked about, right? So it doesn't fit the definition of the transfer of a hydrogen from one thing to another. But, by the Lewis definition, this works, okay? So that's a Lewis acid and base. So explain the formation of NH4 plus from NH3 and H plus in terms of Lewis acid and bases. Okay, so we need to draw the Lewis structure for both of these things. NH4 plus is going to look like, well, actually, I'm sorry, we'll get to that in a minute. NH3 has the lone pair. Okay, now H plus it's kind of weird. Never written the Lewis structure for H plus before. That's it. No electrons. Okay, so you don't have to write any dots on the H plus. So based on that, when those come together to form NH4 plus, which one's the Lewis acid and which one's the Lewis base? Well, which one's the Lewis acid? Let me just ask you that. Okay. So the H plus is the Lewis acid, and the Lewis base, the electron pair donor, is going to be the NH3. Okay. So those come together. I shouldn't put an arrow there. Plus sign there. And we're going to end up forming NH4 plus over here. Okay. And actually, I guess I could have drawn the. Let me do this right. There we go. Okay. Does that make sense? Now, notice something. If I had asked you which one's the acid and which one is the base here, you probably would have told me H plus is the acid, right? Because we know acids have a high concentration of H plus in them. And you might have told me NH3 is the base. We haven't really gotten to talking much about weak acids and weak bases. NH3 is a very commonly known weak base, okay? So this actually fits the Bronsted-Lowry definition of an acid and base also, right? So if it's a Bronsted-Lowry acid and base, it's also going to be a Lewis acid and base, okay? But sometimes it can be a Lewis acid and base without being a Bronsted-Lowry acid and base. So this is Lewis acid and base is just a broader definition, okay? Why did I start talking about this all of a sudden? Well, turns out that's how these complex ions form in the first place, okay, is by these Lewis acid-base reactions. So you've got something like Ag plus, okay? So that silver here, it has lost an electron, right? It's an ion, and so it has an empty orbital, okay? Or, you know, several empty orbitals, because once we talk about transition metals, which the most common metal complexes form with transition metals, we've got, you know, several empty d orbitals most of the time, or, you know, at least partially empty. And so those empty d orbitals are now free to form these metal complexes, okay? And so the silver here, it's going to accept the lone pairs from this NH3, okay? And now you've got a lone pair on either side of the silver. And so you have this Ag NH3-2 complex, okay? Good general rule of thumb, I'll probably come back to this, and it's also on the packet that I'm going to give you tomorrow. If you're trying to figure out how many ligands will form around a central metal atom, usually it's twice the charge on the atom, okay? So notice here, the silver has a 1+ charge, right? And it has 2 NH3s bonded to it, okay? So if you want to know how many ligands are going to form around a central atom, it doesn't always work, okay? But a good general rule of thumb is it's twice the charge on the atom, okay? And actually, this is another example of where that works, right? This copper's a 2+ charge, and there are 4 ammonias bonded to it, okay? So oxidation numbers here, we've talked about this a little bit, figuring out oxidation number. It's been a little while. It's been kind of a long while at this point. But these are usually pretty easy to figure out the oxidation number for, all right? So we've got this copper ammonia metal complex here. And overall, this ion is a 2+ charge, okay? Now, if we look at ammonia, NH3, that's actually a neutral molecule, right? It has no charge. Okay, so because this ammonia has 0 charge, it has a 0 oxidation number. All right. So this 2 plus charge here, it must be coming from the copper, which means the copper must be a 2 plus. Okay, does that make sense? Or if you know that, you can kind of go backwards. If you know the oxidation number, then you can figure out the overall charge on the complex ion. Okay, so let's try one of these. Oxidation number of the central metal in RH NH35Cl NO32. These just kind of get long and ridiculous. So RH is our central metal. Okay, central metal is listed first in the complex ion. Well, a couple of things here. We have to look at this as an ionic compound, right? This is the cation, this is the anion. Okay? What's the charge on the cation here? Now, the charge on the overall compound is neutral, but what's the charge on just this piece right here? I'm hearing it. 2 plus. Okay, and the reason we know that is because it took 2 nitrates to make it a neutral compound, right? And each nitrate has a 1 minus charge. Okay, so overall, we've got this is our complex metal ion here. Okay, so that helps a little bit. Okay, we know that we have an overall 2 plus charge on this ion. So then we just have to figure out what the charge on everything else is besides the metal. And that'll help us to decide what the oxidation number is in the metal. What charge does NH3 have? It's neutral, right? So it has 0 charge. So 5 times 0 is still 0. Okay, what charge does the chloride have? Always a 1 minus for chloride, right? So in order to have an overall 2 plus charge, what charge does this RH need to have? Plus 3. Okay, so there we go. RH here, well, I don't want to write it like that necessarily because this is covalently bonded, so talking about charge is kind of weird here, but we're talking about oxidation here, okay? It has an oxidation number of plus 3. So that's how you would figure that out, okay? A complex ion contains chromium-3 bound to 4 water molecules and 2 chloride ions. What is its formula? Okay, now it says specifically here that it's bound to 4 water molecules and to 2 chloride ions. Right? So what's its coordination number, first off? Good, 6, because it's bound to 6 different things. Okay, so we've got chromium-3 here. They're already telling us that the chromium has a 3 plus charge. All right, so this complex is going to look like this. Cr, and then we've got 4 water molecules, so we're going to write H2O 4 and 2 chloride ions, so then outside of that we're going to write Cl2. And what they want to know is what's the charge, the overall charge on the ion here. Okay, so this is actually not, I think it's easier to go this way than the other way. What charge is our chromium here? It's a 3 plus because it's chromium-3. That's what the Roman numeral tells us. What charge does water have? Water is also a neutral compound, right? So 0 times 4 equals 0. And then each of the chlorides is a minus 1. There's 2 of them, so that's a minus 2 overall. So what's our overall charge on this ion here? It's going to be 1 plus. Or you can just put a plus there. You don't have to put 1 plus. Okay? So that's how you figure out those oxidation numbers. All right. Coordination number. We're going to talk a little bit more about this now. We've already mentioned this, okay? Some metals consistently have the same coordination number. Chromium-3 and cobalt-3 always have a coordination number of 6. Now, you could also figure that out based on the general rule that I told you, right? Okay? Each of those has a 3 plus charge. So things with a 3 plus charge tend to have a coordination number of 6. They tend to be bonded to 6 different things, okay? Things with a charge of plus 2 tend to be bonded to how many things? 4. You just double the charge, okay? And then things with a plus 1 tend to be bonded to 2 things. Now, again, there are exceptions to that rule, okay? But I think if you know that rule, then you're going to be fine on the equations that you have to write on the AP exam. Okay, most commonly encountered are 4 and 6 because the most common charges on transition metals are +2 and +3. Okay. Geometries, the two common geometries here, when you have a coordination number of 4, it could either be a tetrahedral arrangement, or you could have a square planar arrangement if there's lone pairs on the top and the bottom. Okay. Top and the bottom of the metal, I mean. Almost all of the 6 coordination complexes have an octahedral geometry, right? Because that's, I mean, that's really the best way to get everything as far away from each other as possible, is to have that octahedral arrangement, okay? And we really can't get more than 6 atoms around any central atom most of the time, okay? All right, so here's an example of a free response question you might have on the AP exam here. Excess concentrated aqueous ammonia is added to a solution of nickel-2 nitrate, leading to the formation of a complex ion. Here's the nice thing on the AP exam. They will always tell you now, on the equation writing section, they will tell you this is going to form a complex ion, okay? So you don't have to necessarily identify that. You don't have to recognize that's what's going to happen, because they're telling you that that's going to happen, okay? We want to write the balanced chemical equation for this reaction. So we've got nickel-2 nitrate. What's the formula for nickel-2 nitrate here? NO32, right? NO32. That's a solution, so that's aqueous. Okay. Now remember, on this section of the AP exam, it has to be a net ionic equation. All right. So we're gonna write this first, and then we're gonna change it to a net ionic after that. So NiNO32 aqueous plus excess ammonia, right? So we're just adding NH3 to this, and this is also aqueous. Now this is not split apart in water, okay? So even though it's aqueous, we can't split that apart when we write our net ionic equation, okay? Because it's not an ionic compound. So if we're going to form a metal complex here, anybody want to take a stab at what that's going to look like? NiNH3 2. Okay. That's really close. I'm going to guess something else here, based on the fact that the charge is a 2+. I'm going to say that the nickel probably has a coordination number 4 at the end, right? Because we're going to double the charge. So, like I said, you were pretty close on this one, but you'd have to write this in brackets. It would be NiNH3 4. Okay, now what charge is this thing going to have now when it forms an ion? Okay, what charge does the nickel have? 2+. What charge does the ammonia have? Now, the ammonia, it's a neutral compound, right? So it has a charge of 0. Okay. Now the nitrate has a 1-, right? But the ammonia has a 0. So this is overall going to be a 2+. Okay. Now I sort of split these apart over here, right? And then we're going to have our nitrates over there as well. But who cares about the nitrate? Because when you're writing your net ionic equation, this is going to be split apart anyway, right? Okay. So maybe a better way to write this is just from the very beginning. This is nickel 2+ and NO3-, right? But this does nothing in the course of the reaction, okay? So our net ionic equation here would be nickel 2+ plus NH3 gives us NiNH3 2+, gives us that complex ion. Now am I done? Why am I asking that question? Is this balanced? You know what? This is really easy to balance, okay? The only thing that's unbalanced here is my ammonia, right? So if I just put a 4 right here, then we're good. Okay? Yeah. This is fun stuff. Okay, so then they're going to ask which of the reactants is acting as a Lewis acid. Okay? So based on what we just learned about Lewis acids and bases here, which one is going to be the... Remember, Lewis acids are the electron pair acceptors. Okay? Which one's going to be the electron pair acceptor? Yeah, that's the one that, you know, has these empty orbitals. So the nickel is going to be the electron pair acceptor. The NH3, remember, if we draw the Lewis structure for NH3, it has an extra electron pair there that it can donate. So that's going to be the Lewis base. All right? So the Lewis acid here is going to be the Ni2+. Okay? And that is usually the extent of what they ask you on the AP exam regarding complex ions. Now, I'm going to go into a lot more detail than that right now. Okay? Just want you to be aware of this, that sometimes there can be what's called these polydentate ligands, okay? And all that means is they actually connect to the central atom at 2 different points, okay? So, ethylene diamine, also called EN, okay? Make sure you make a note of that for the take-home quiz that I'm giving you, okay? Because that one's in there. Notice there are only 3 of those attached to this cobalt, but because on the ethylene diamine, if you look at this, it's got 2 nitrogens in it. Each of these nitrogens has a lone pair on it. So this can actually be a Lewis base in 2 different spots on the same molecule, okay? So notice here, this is all one molecule, okay? But it's connected to the cobalt at 2 different places, all right? And so you actually have a coordination number of 6 here, even though there's only three molecules attached to the central atom, because each molecule is connected to the central atom in 2 separate spots. Does that make sense? Okay. This is connecting here and here to the central atom. Well, this is all the same molecule. So you only need 3 of those to make a coordination number of 6. Okay? So that can happen sometimes. Ethylene diamine tetraacetate, or EDTA, actually has 6 donor atoms in the 1 molecule. Okay? EDTA basically has the ability to completely surround this cobalt and connect to it at 6 different points. This is 1 molecule connecting in 6 different locations onto a central atom. Okay? So this thing, I mean, it completely surrounds the central atom and connects to it, and so then the cobalt's full. It can't, you know, bond to any other atoms at that point. Okay? So this is CO, cobalt, EDTA, or the full name would be cobalt ethylene diamine tetraacetate, right? Ion. All right. These chelating agents, they're usually more stable complexes. For whatever reason, I guess just the wrapping around of 1 molecule around a central atom forms a more stable arrangement somehow than if you have the monodentate ligands, the monodentate being like water or ammonia, the ones we've been talking about so far. Okay. So what they can do, actually, these chelating agents, okay, these things that can bond to the central atom at more than 1 point, they can actually surround these metal atoms and make them completely inactive. Okay, so if you have a metal you're worried about, maybe its reactivity with other things, you put one of these chelating agents in there, it completely surrounds those metals and takes them out of commission. Now those metals have no way to react with anything else, okay, which is kind of a useful thing. So phosphates actually can tie up, because these have several different places where they can bond to, now this is showing with sodium, but calcium and magnesium in your hard water, that can actually soften your water. Okay, it takes those Ca and Mg2+ ions out of commission. All right. Some other practical application here. Chlorophyll does this. Okay. So chlorophyll in plants actually is a tetradentate ligand. So, I mean, this is a huge molecule here, but you've got 4 magnesium with a coordination number 4 here. It's surrounded by 4 other atoms, okay, and they're covalently bonded. Other examples here. So porphyrins kind of look like this, okay? And again, they just left this part blank because, you know, insert your metal atom here, whatever metal atom we're talking about, okay? So this is a general structure, and depending on what metal atom is here, that determines what the molecule actually is, okay? And you've got heme, like heme from hemoglobin in your blood, and also chlorophyll. These are porphins, okay? So that's a special class of molecule that's very important in organic chemistry. All right, nomenclature. I'm actually going to skip over this for now because this is on the packet that you have for tomorrow, okay? So, and it actually does a much more thorough job of teaching that from the packet. We will talk about all this on Monday when I get back, okay? And we'll do as much practice of this as we need to. So let's skip over that for now, because there's one other thing that I really want to get to. And these things, I mean, if you look at the names of these things, it's actually, the rules for naming them are very, very, very logical, okay? But it looks crazy, okay? I mean, so you get these things, if you know how to name these things, everyone's going to think you're super smart, okay? And they're really not that hard, but they look unbelievably complicated, okay? So, pentaamine chlorocobalt 3 chloride, you know. Yeah, well, I was working with pentaamine chlorocobalt 3 chloride in the lab the other day. You know, everyone's going to be like, what? You're going to be very impressed. Or they might just walk away. Be like, I don't want to talk to you anymore. Okay, again, all of this is in your notes. So the one last thing that I wanted to talk about here before we get done is something that, again, I just sort of tacked in here because I didn't know where else to put it exactly. But we need to talk about the idea of paramagnetic versus diamagnetic versus ferromagnetic, okay? Because I think that terminology has sort of popped up on one of your AP packets before, and you didn't really know what it was. What's diamagnetic versus paramagnetic? And this is actually a fairly simple idea, okay? I just wanted to throw it in here because we were talking about transition metals, so this kind of fits, okay? Transition metals we know can have more than one oxidation state. I mean, that's why we have to use Roman numerals when we name them, right? Because they can have a +2 or a +3 sometimes. That has to do with their loss of s and d electrons, all right? So transition metals are going to lose their s electrons first, and then they're going to lose their d electrons after that, okay, if they lose any additional electrons. So that kind of explains why these things lose electrons the way they do. I know we've talked about that already this year, so I'm just reminding you of that, okay? Again, a lot of these, the metal complexes or transition metals in general, will form very brightly colored solutions. And a lot of them, the transition metals, have significant magnetic properties, okay? Some of them do, some of them don't. Now, when we talk about diamagnetic elements, that doesn't just have to be transition metals, okay? But this is just kind of a good place to talk about this with transition metals. If you have a diamagnetic element, all the electron spins are paired, okay? All that means is the orbitals are all full, okay? So an example of that would be something like magnesium, right? Because if you think about the electron pairing on magnesium, so magnesium has, you know, it has 1s, 2s, 2p, all of that, and then its 3s orbital, that's its last orbital, right? And it has 2 electrons in that last orbital. So all of its orbitals are completely full of electrons. It has no unpaired electrons, right? Does that make sense? So when it has no unpaired electrons, it's going to be diamagnetic. And that's, if they ever ask you a question about that on the AP exam, that's really all you need to know, okay? So there's no net magnetic moment. In other words, there's no overall magnetism to that because the electron spins are basically canceling each other out, okay? So when you put these into a magnetic field, they're slightly repelled by the magnet. They're not going to be attracted to it, okay? Paramagnetic, there are some unpaired spins. So an example of that, and again, it doesn't even have to be a metal atom that's paramagnetic. We could have something like nitrogen, right? So with nitrogen, you've got your last set of orbitals. You've got your 2s orbitals here. But then your last set of orbitals is your 2 p's. 2 s's are full. But then we've got some unpaired electrons in the 2p orbitals, right? So that's going to be paramagnetic, okay? There are some unpaired spins there. Now, these unpaired spins, if you look at these atoms, they're going to be randomly arranged, okay? So it's not like they line up or anything. And so that means that overall nitrogen is not going to exhibit metallic properties normally, right? It's just a gas, it's not metallic. But if you put it into a magnetic field, then that can actually, all these things can line up, okay? And then it actually does exhibit some magnetic properties, okay? And that's because it's got some unpaired electrons. So if you can get all those electrons sort of facing the same direction, or those magnetic moments all facing the same direction, then you would exhibit some magnetism there, okay? Ferromagnetic substances, they're already all lined up. They're already all lined up, okay? And so you don't even have to put these into a magnetic field. These electron spins are already lined up with one another, okay? And so that's what makes something magnetic even if it's not put into a magnetic field. So things like iron, they're going to be attracted to magnets, you know, regardless, okay? And so I just want you to know the difference between those three. So then you might get a question like this: which of the following be expected to be diamagnetic and paramagnetic? This is the only question I would imagine you would be asked about this particular topic on the AP exam. So which one of these would be diamagnetic? Okay, beryllium would be diamagnetic, right? Because beryllium has no unpaired electrons. What else? Helium would also be, right? Because it has no unpaired electrons. So these are both dia. And then which ones would be paramagnetic? The other two, obviously. Okay, lithium has one unpaired electron, so that's going to be para. And then nitrogen has 3 unpaired electrons, so that's also going to be para. Okay? Whew, made it. Alright, so like I said, we'll do a lot more practice with the complex ions in class. I know that's a complicated topic. We've got a couple of days to work on it. We'll see you in class.